Bismillah ar-Rahman ar-Rahim. In the section 2, I think, we defined reference set based on the CCR model in weighted form. Here, the reference set is defined based on the envelope in form of the CCR model. For an inefficient DMU, say DMU-O, we define its reference set EO based on the Maxwell-like solution as obtained in phase 1 and 2 by EO is J that lambda star J are greater than 0 for J from 1 to n. Note that this solution is defined based on an optimal solution of DLPO as we defined it before. So since the model can have different optimal solution, alternative optimal solution, so for each optimal solution we may have EO and as exercise, please compare this set with the set of EO which was defined before. Indeed, we defined reference set based on an optimal solution to the weighted form of the model, here based on an optimal solution of the envelopment form. As an exercise that you should do and send to me, show what is the relation between these two sets. Now if we refer to the constraints of the DLPO, which was solved and theta star was its optimal objective function value and lambda star, s minus s star and s plus s star its optimal value for the other variables. Since each optimal solution is feasible, if you put this optimal solution in the constraints, you see we have theta star xo is equal to the summation of xj lambda j star j from 1 to n, but since only the j's that belongs to EO have lambda j positive, the others are 0, so we can write it instead of j from 1 to n, the summation of xj lambda j star, j belongs to EO, and this is plus s minus s star. For the output constraints, if we put the optimal solution, we have the second relation. This can be interpreted as follows. Note that since theta star is less than or equal to 1 and the variables all are non-negative, so we have obviously xo is greater than or equal to theta star xo minus s star, that is this summation, and a positive combination of the inputs of DMUs in the references. This means XO, the input vector of DMUO, is bigger than or equal to, this is technical, and this is mix inefficiency. So we have technical minus mix inefficiency. And this is also a positive combination of observed input values. For the outputs, we have YO is less than or equal to YO plus S positive star. And this is also from the constraints, and we have write it here. This is equal to this combination of the outputs of the other DMUs. So we have YO is less than or equal to, this is observed outputs, and this is shortfalls. Again, it is a positive combination of observed, of course, output values. These relations suggest that the efficiency of DMUO, indeed XO and YO for DMUO, can be improved if the input values are reduced radially by the ratio theta star. Indeed, if we first multiply theta star by XO, this, since theta star is less than or equal to 1, this is reducing the inputs radially. With the same ratio of theta star, and the input excess recorded in S minus star are eliminated after reducing radially. We reduce also with these values if they are not 0. Similarly, efficiency can be attained if the output values are augmented by the output shortfalls in S plus S star. Thus, this is also can be solved from here. So we have a method for improving an inefficient DMU that accords with definition 3.2. The gross input improvement, which is named delta XO, and the output improvement delta YO can be calculated from delta XO is the observed minus the new values of XO, that was this, first reducing radially and then non-radially, and is the positive combination of the other DMUs with the weights given here from the optimal solution. So we have XO minus this, that is equal to this value, and from the outputs are only added by S plus as a star, so their difference, the observed and the new outputs, the outputs of the projection, their difference is S plus star. So delta YO is S plus star, means we can add the output with splat star to give a better combination of inputs and outputs. Here we have a formula for improvement, which is called the CCR projection. Indeed, the CCR projection is the DMU, a point in the production function that is compared with the DMUO and shows how inefficient it is, and it is efficient. We will prove it later. The inputs of DMUO, if it can be better, it should be we should XO minus delta XO, that is these values. Of course, we have defined this before also. This means this combination of this value is the input projection of the inputs of DMUO, and the outputs are this, which is obtained by adding delta Y O to Y O, that is this. It is obvious that the inputs are less than or equal to inputs of the observed DMUO, and the outputs are bigger than or equal to the observed outputs. So we can improve the efficiency of DMUO by changing in inputs to this X hat O and the outputs to Y hat O, Y or Y. Now we give some theorems on CCR efficiency. The first one is theorem 3.2. The improved activity X hat O and Y hat O defined by 3.22 and 3.23 is CCR efficient. This X hat O and Y hat O was defined as this. Of course, X hat O also is this value, the positive combination of the inputs of DMUs in the reference set, and the Y hat O is also this combination. Now we want to show this as a DMU is efficient by using the envelope model. The efficiency of each DMU, here X hat O and Y hat O, is evaluated by solving the LP problem below. Note that we named the LP problem in envelopment form, which evaluate DMUO with XO and YO as its inputs and outputs. DLPO, here for the projection we name it DLPE. So we first should minimize theta when with this constraints, subject to these constraints. And it here we only put instead of x or x hat o, and instead of y or y hat o. This is the CCR modeling envelopment for to evaluate x hat o and y hat o. By the definition, we want to show this is CCR efficient. By the definition, we should prove first that the optimal objective function value of this model is 1, and second, all the slags in the max slag optimal solution is 0. First, so let an optimal or arbitrary if we show that for each optimal solution, any arbitrary optimal solution, theta is 0 and the slags, optimal slags are 0, is equivalent to show this is true for max slag. So there is no difference if we give an arbitrary optimal or max slag solution. So let theta hat, lambda hat, s hat minus and s hat plus be an optimal solution or max slag solution of this model DLP E. Note that theta equal to 1, lambda, if we put it lambda star, s minus 0, s plus 0 is a feasible solution for DLPE. And it is feasible for DLPE since by the definition we have x hat o is x lambda star, y hat o is y hat o here, y hat o is equal to y lambda star. This is from the definition we had before. If we put this to the DLPE model, it will be show that this, indeed this shows this is it shows that this is a feasible solution for DLPE. And since this was its optimal value, this is feasible, this is optimal, and the model is minimization, so we have theta hat is less than or equal to 1. We name it a star. Now, by inserting the formula 3.22 and 3.23 into the constraints we have, and it we put instead of x at o, it was equal to theta star xo minus s minus a star. So we put instead of x hat o, it's equivalent from here this, and instead of y hat o this, we know this is the optimal solution of this model, so it is feasible and satisfies the constraints. We put in the constraints these values, and instead of x hat o and y hat o, the equivalent values from 3.22 and 3.23. So we have this relations. Now we can also write this solution as this by putting theta hat, theta star, theta, new variable, define new variable, and putting this as s mat minus. Note that this is bigger than or equal to 0 because all of these values are non-negative, and by I'm putting s mat plus equal to this, we have, which is also non-negative, we have this. Now compare this with the constraints of DLPO, that is DLPO as we defined it before, it is minimizing theta with these constraints. So it can be seen that these values are feasible for DLPO. So again, since the optimal value of minimization is always less than or equal to any optimal feasible objective value, so we have theta star is less than or equal to theta mat, that is theta hat by theta star as we defined it before. And since theta star is bigger than 0, we have theta hat from this relation by removing theta star from both sides. We have theta hat is greater than or equal to 1. We name this 2 star. We showed before theta star is less than or equal, theta hat is less than or equal to 1. Here theta hat is bigger than or equal to 1, so it is equal to 1, and indeed this star from a star and to a star, we have theta hat equals to 1. This is the first condition of the CCR efficiency. Note that this is a feasible solution, and since theta hat was proof that is equal to 1, so theta mat is equal to theta star from here. So we have theta hat is equal to theta star. This shows this is also not only a feasible but also an optimal solution of this model. But theta star, lambda star, s minus star, s plus star was max slack optimal solution for DLPO because we had this assumption to define the projection. This is Max's-like and this is another optimal solution that is not necessarily Max's-like. So the optimal, because the phase 2 is maximization, this is Max's-like, so this is the optimal objective function value of phase 2 model. So it is bigger than or equal to the objective function of any feasible solution. By putting equivalent value of these from here, we have this. If we remove ES minus star and ES plus star from both sides, we have this, and since the slags are non-negative, we should have all the slags equal to 0. So we show both conditions for CCR efficiency in definition 3.2. First, the objective function value of the model is 0, and then its optimal slags for Max's-like solution or any arbitrary optimal solution is equal to 0. This shows that x hat O and y hat O is CCR efficient by the definition.